Welcome friends. In this module we discuss more problems on Poisson and geometric random variables. First of all, let us revise. Poisson distribution. A random variable x is said to follow a Poisson distribution if its probability mass function is of the form f of x equal to e raised to minus lambda, lambda raised to x by x factorial for x equal to 0, 1, 2, etc. up to infinity for lambda greater than 0 and f of x is equal to 0 otherwise. For a random variable x, follow binomial distribution with parameters n p when n is indefinitely large, that is n tends to infinity, p the probability of success is indefinitely small, that is p tends to 0. Let n p equal to lambda, which is finite, then x can be considered as a Poisson random variable. Geometric distribution. Let x denote the number of failures preceding the first success when a random experiment with only two possible outcomes, success and failure, repeated till the first success occurs. Probability of success p remains unchanged from trial to trial, then x is the random variable following geometric distribution with the following PMF. F of x equal to q raised to x into p for x equal to 0, 1, 2, etc. and equal to 0 otherwise, where q plus p equal to 1 and 0 less than p less than 1. Problem 1. In a city, if the probability of a person suffers from TB is 0.0008, find the probability that out of 4,000 persons, number 1, no person, number 2, at least one person will suffer from the disease. Solution. Let x denote the number of TB patients out of 4,000 persons. The probability of a person suffers from TB is 0.0008. Here, number of individuals tested is large and the probability p of occurrence of TB is infinitesimal. Hence, x can be treated as a Poisson random variable with parameter lambda equal to n into p, that is equal to 4000 into 0.0008, that is equal to 3.2. Now, probability of no person will suffer from the disease equal to p of x equal to 0, that is equal to e raised to minus 3.2, 3.2 raised to 0 by 0 factorial, that is equal to e raised to minus 3.2, that is equal to 0.0408. Probability of at least one person will suffer from the disease, that is equal to p of x greater than or equal to 1, that is equal to 1 minus p of x less than 1, that is 1 minus p of x equal to 0, that is 1 minus e raised to minus 3.2, 3.2 raised to 0 divided by 0 factorial, that is equal to 1 minus e raised to minus 3.2, that is 0.9592. Problem 2. The number of visitors to a clinic follows a Poisson process at the rate of 1.2 per minute between 4 p.m. and 5 p.m. Find the probability that the number of visitors between 4:30 p.m. and 4:35 p.m. is number 1 exactly 6, number 2 less than 3, number 3 at least 5. Solution. The number of visitors to a clinic is at the rate of 1.2 per minute between 4 p.m. and 5 p.m. Hence, we can consider the average visitors in 5 minutes between 4:30 p.m. and 4:35 as 1.2 into 5, that is equal to 6. Thus, p of x equal to some small x, that is equal to e raised to minus 6, 6 raised to x by x factorial for x equal to 0, 1, 2, etc. Probability of number of visitors between 4:30 p.m. and 4:35 p.m. is exactly 6, that is equal to p of x equal to 6, that is e raised to minus 6, 6 raised to 6 by 6 factorial that is equal to 0.1606. Probability of number of visitors between 4:30 p.m. and 4:35 p.m. is less than 3, that is p of x less than 3, that is equal to p of x equal to 0 plus p of x equal to 1 plus p of x equal to 2, that is equal to e raised to minus 6, 6 raised to 0 by 0 factorial plus e raised to minus 6, 6 raised to 1 by 1 factorial plus e raised to minus 6, 6 square by 2 factorial, that is equal to 0.0025 plus 0.0149 plus 0.0446, that is equal to 0.062. Probability of number of visitors between 4:30 p.m. and 4:35 p.m. is at least 5, that is equal to p of x greater than or equal to 5, that is 1 minus p of x less than 5, that is 1 minus of p of x equal to 0 plus p of x equal to 1 plus p of x equal to 2 plus p of x equal to 3 plus p of x equal to 4, that is 1 minus of e raised to minus 6 into 6 raised to 0 by 0 factorial plus e raised to minus 6 into 6 raised to 1 by 1 factorial plus e raised to minus 6 into 6 square by 2 factorial plus e raised to minus 6 into 6 cube by 3 factorial plus e raised to minus 6 into 6 raised to 4 divided by 4 factorial, that is equal to 1 minus of 0.0025 plus 0.0149 plus 0.0446 plus 0.0893 plus 0.1339, that is equal to 0.7148. Problem 3. If x follows Poisson distribution with the parameter unity, show that mean deviation about mean is 2 by e time the standard deviation. Solution. Mean deviation about mean of x is expectation of modulus of x minus expectation of x. Given x follow Poisson distribution with parameter 1, hence expectation of x is equal to 1 and standard deviation of x is equal to 1. Now, the mean deviation about mean of x is expectation of modulus of x minus 1. Expectation of modulus of x minus 1 equal to summation x from 0 to infinity modulus of x minus 1 into f of x. Here f of x is equal to e raised to minus 1, 1 raised to x by x factorial, that is equal to e raised to minus 1 by x factorial for x equal to 0, 1, 2, etc. Thus, expectation of modulus of x minus 1 equal to summation over x from 0 to infinity modulus of x minus 1 into e raised to minus 1 by x factorial, that is equal to 1 into e raised to minus 1 by 0 factorial plus 0 into e raised to minus 1 by 1 factorial plus 1 into e raised to minus 1 by 2 factorial plus 2 into e raised to minus 1 by 3 factorial plus etc. That is equal to e raised to minus 1 into 1 plus 1 by 2 factorial plus 2 by 3 factorial plus 3 by 4 factorial plus etc. That is equal to e raised to minus 1 into 1 plus 2 minus 1 by 2 factorial plus 3 minus 1 by 3 factorial plus 4 minus 1 by 4 factorial plus etc. That is e raised to minus 1 into 1 plus 2 by 2 factorial minus 1 by 2 factorial plus 3 by 3 factorial minus 1 by 3 factorial plus 4 by 4 factorial minus 1 by 4 factorial plus etc. That is e raised to minus 1 into 1 plus 1 minus 1 by 2 factorial plus 1 by 2 factorial minus 1 by 3 factorial plus 1 by 3 factorial minus 1 by 4 factorial plus etc. That is e raised to minus 1 into 2, that is 2 divided by e into 1, that is 2 by e into standard deviation of x. Next problem. The probability that an individual suffers a bad reaction from a medicine is 0.004. Out of 200 individuals admitted the medicine, find the probability that 1. Exactly 5, 2. More than 3, 3. None suffers from bad reaction. Solution. Let x denote the number of individuals suffering from bad reaction. We have 200 individuals and hence the possible values of x are 0, 1, 2, etc. 200. Also given the probability of an individual to suffer from bad reaction is 0.004. In this case, x can be considered as a binomial random variable with parameters n equal to 200 and p equal to 0.004. Observe that n is large and p is small, hence x can be considered as a Poisson random variable with parameter lambda equal to n into p, that is 200 into 0.004, that is equal to 8 to solve the problem. 1. Probability of exactly 5 suffers from bad reaction equal to p of x equal to 5, that is e raised to minus 8 raised to 5 by 5 factorial, that is 0.0916. 2. Probability of more than 2 suffers from bad reaction, that is equal to p of x greater than 2, that is equal to 1 minus p of x less than or equal to 2. That is 1 minus of p of x equal to 0 plus p of x equal to 1 plus p of x equal to 2. That is 1 minus of e raised to minus 8 raised to 0 by 0 factorial plus e raised to minus 8 raised to 1 by 1 factorial plus e raised to minus 8 square by 2 factorial. That is 1 minus of e raised to minus 8 plus 8 e raised to minus 8 plus 32 e raised to minus 8. That is 1 minus 41 e raised to minus 8, that is 0.9861. 3. Probability of none suffers from bad reaction, that is equal to p of x equal to 0, that is e raised to minus 8 raised to 0 by 0 factorial, that is e raised to minus 8, that is 0.00034. Problem 5. X follows Poisson lambda and 2 times p of x equal to 0 equal to p of x equal to 2. Find number 1 p of x less than 2, number 2 p of 1 less than x less than 4. Solution. Given x follow Poisson lambda, hence p of x equal to small x is e raised to minus lambda raised to x by x factorial for x equal to 0, 1, 2, etc. Given 2 times p of x equal to 0 is equal to p of x equal to 2. Thus, 2 times e raised to minus lambda into lambda raised to 0 by 0 factorial equal to e raised to minus lambda into lambda square divided by 2 factorial. That is 2 into e raised to minus lambda equal to e raised to minus lambda into lambda square divided by 2. This implies lambda square equal to 4. Since lambda greater than 0, we get the value of lambda as 2. Now, number 1 p of x less than 2, that is equal to p of x equal to 0 plus p of x equal to 1, that is equal to e raised to minus 2 raised to 0 divided by 0 factorial plus e raised to minus 2 raised to 1 divided by 1 factorial, that is equal to 3 into e raised to minus 2, that is 0.4059. Number 2 p of 1 less than x less than 4, that is equal to p of x equal to 2 plus p of x equal to 3, that is e raised to minus 2 square by 2 factorial plus e raised to minus 2 cube divided by 3 factorial, that is 4 into e raised to minus 2 by 2 plus 8 into e raised to minus 2 divided by 6, that is 10 into e raised to minus 2 by 3, that is equal to 0.451. Problem 6. If x has a Poisson distribution with parameter lambda, show that the distribution function of x is given by capital F of x, that is equal to 1 divided by gamma of x plus 1 integral from lambda to infinity e raised to minus t raised to x dt for x equal to 0, 1, 2, etc. Solution. Given x is a Poisson random variable with parameter lambda, then p of x equal to some small x, that is equal to e raised to minus lambda raised to x by x factorial for x equal to 0, 1, 2, etc. Let I x is equal to 1 by gamma of x plus 1 integral from lambda to infinity e raised to minus t into t raised to x dt. Consider t raised to x as the first function, then Ix is equal to 1 by x factorial into t raised to x into e raised to minus t by minus 1 over the interval from lambda to infinity minus of integral from lambda to infinity x into t raised to x minus 1 into e raised to minus t divided by minus 1 dt. That is equal to e raised to minus lambda, lambda raised to x by x factorial plus 1 by x minus 1 factorial into integral from lambda to infinity t raised to x minus 1 into e raised to minus t dt. This implies Ix is equal to e raised to minus lambda into lambda raised to x by x factorial plus Ix minus 1. Integrating Ix minus 1 as above, we get Ix minus 1 equal to e raised to minus lambda, lambda raised to x minus 1 by x minus 1 factorial plus Ix minus 2. Proceeding like this, finally we get Ix is equal to e raised to minus lambda, lambda raised to x by x factorial plus e raised to minus lambda, lambda raised to x minus 1 by x minus 1 factorial plus etc. plus I0. But I0 equal to 1 divided by gamma 1 integral from lambda to infinity e raised to minus t into t raised to 0 dt. That is integral from lambda to infinity e raised to minus t dt. That is minus of 0 minus e raised to minus lambda, that is equal to e raised to minus lambda. Hence, Ix is equal to e raised to minus lambda, lambda raised to x by x factorial plus e raised to minus lambda, lambda raised to x minus 1 by x minus 1 factorial plus etc. plus e raised to minus lambda. That is equal to p of x equal to small x plus p of x equal to x minus 1 plus etc. plus p of x equal to 0. That is equal to p of x less than or equal to x, that is equal to capital F of x. So, capital F of x is equal to 1 divided by gamma of x plus 1 integral from lambda to infinity e raised to minus t t raised to x dx for x equal to 0, 1, 2 etc. Problem 7. During a typical football game, a coach can expect 2.3 injuries. Find the probability that the team will have at most one injury in this game. Solution. Let x denote the number of injuries which can be assumed as Poisson random variable. A coach can expect 2.3 injuries, that means lambda equal to 2.3. Probability that the team will have at most one injury is p of x less than or equal to 1. P of x less than or equal to 1 equal to p of x equal to 0 plus p of x equal to 1. That is e raised to minus 2.3 into 2.3 raised to 0 by 0 factorial plus e raised to minus 2.3 raised to 1 by 1 factorial. That is 3.3 e raised to minus 2.3, that is equal to 0.331. Problem 8. For a random variable x following Poisson distribution, the coefficient of variation is 50%. Find p of x greater than 1. Solution. Coefficient of variation CV equal to standard deviation by arithmetic mean into 100. For x follow Poisson lambda, mean equal to lambda and standard deviation equal to root lambda. Hence, CV equal to root lambda divided by lambda into 100, that is equal to 1 by root lambda into 100. Given 1 by root lambda into 100 equal to 50. This implies 1 by root lambda equal to 1 by 2. This implies lambda equal to 4. P of x greater than 1 equal to 1 minus p of x less than or equal to 1, that is 1 minus of p of x equal to 0 plus p of x equal to 1, that is equal to 1 minus of e raised to minus 4 raised to 0 by 0 factorial plus e raised to minus 4 raised to 1 by 1 factorial, that is 1 minus 5 e raised to minus 4, that is equal to 0.9085. Problem 9. From a deck of 52 cards, draw cards at random with replacement until an ace is shown. What is the probability that at least 5 draws are needed? Solution. Since the deck of 52 cards contains 4 ace cards, the probability of getting an ace card is 4 by 52, that is 1 by 13. Cards are taken with replacement and hence the probability of getting an ace remains same for all the trials. Let x denote the number of trials before getting the first ace card. Then x follows geometric distribution with parameter p equal to 1 divided by 13. F of x is equal to 12 by 13 raised to x into 1 by 13 for x equal to 0, 1, 2, etc. Probability that at least 5 draws are needed for the first ace is denoted by p of x greater than or equal to 5. P of x greater than or equal to 5 equal to p of x equal to 5 plus p of x equal to 6 plus p of x equal to 7 plus etc. That is 12 by 13 raised to 5 into 1 by 13 plus 12 by 13 raised to 6 into 1 by 13 plus 12 by 13 raised to 7 into 1 by 13 plus etc. That is 12 by 13 raised to 5 into 1 by 13 into 1 plus 12 by 13 plus 12 by 13 square plus etc. That is 12 by 13 raised to 5 into 1 by 13 into 1 minus 12 by 13 the all raised to minus 1. That is 12 by 13 raised to 5, that is 0.6703. Problem 10. The chance of a student to win a test is 0.2 and assumed remains same for all attempts. If he decides to compete until success, what is his chance to win the test by fifth attempt? Also find the expected number of attempts to win the test. Solution. Let x denote the number of failures before the success. Since the probability of success in each attempt is 0.2, x follow geometric distribution with parameter p equal to 0.2. F of x equal to 0.8 raised to x into 0.2 for x equal to 0, 1, 2, etc. Probability of winning the test by fifth attempt, that is equal to probability of getting 4 failures before first success. That is equal to p of x equal to 4, that is 0.8 raised to 4 into 0.2, that is equal to 0.082. Expected number of failures before success is q by p, that is equal to 0.8 by 0.2, that is 4. Hence, the expected number of attempts to success is 4 plus 1, that is 5. Problem 11. If x is a geometric random variable with parameter p, show that 1. Probability of x is odd and probability of x is even are respectively q divided by 1 plus q and q square divided by 1 plus q. Solution. X follow geometric distribution with parameter p, then f of x equal to q raised to x into p for x equal to 0, 1, 2, etc. Probability of x is odd, that is equal to p of x is equal to 1 plus p of x is equal to 3 plus p of x equal to 5 plus p of x equal to 7 plus etc. That is q raised to 1 into p plus q cube into p plus q raised to 5 into p plus etc. That is equal to p into q into 1 plus q square plus q raised to 4 plus etc. That is equal to p into q into 1 minus q the all raised to minus 1 plus 1 plus q the all raised to minus 1 all divided by 2. That is equal to p q into p raised to minus 1 by 2 plus 1 plus q all raised to minus 1 divided by 2. That is p q into 1 divided by 2 p plus 1 divided by 2 into 1 plus q. That is p q into 1 plus q plus p all divided by 2 p into 1 plus q. That is equal to q into 1 plus q plus p divided by 2 into 1 plus q. That is equal to q into 1 plus 1 divided by 2 into 1 plus q. That is q into 1 divided by 1 plus q, or that is equal to q divided by 1 plus q. Probability of x is even, that is equal to p of x equal to 2 plus p of x equal to 4 plus p of x equal to 6 plus p of x equal to 8 plus etc. That is equal to q square into p plus q raised to 4 into p plus q raised to 6 into p plus etc. That is p q into q plus q cube plus q raised to 5 plus etc. That is equal to p q into 1 minus q the all raised to minus 1 minus 1 plus q all raised to minus 1 all divided by 2. That is p q into p raised to minus 1 by 2 minus of 1 plus q all raised to minus 1 by 2. that is equal to pq into 1 divided by 2p minus 1 divided by 2 into 1 plus q, that is equal to pq into 1 plus q minus p divided by 2p into 1 plus q, that is equal to q into p plus q minus p divided by 2 into 1 plus q, that is q into 2q divided by 2 into 1 plus q, that is equal to q square divided by 1 plus q. More problems arising in various real life situations involving the discrete probability distributions, Poisson distribution and geometric distribution are discussed in this session. Applications of these distributions are illustrated through the problems discussed. Before we attend the next unit, please try to answer the following questions. 1. If the probability of a person suffers from a disease is 0.001, find the probability that out of 5,000 persons, number 1 less than 5, number 2 more than 3 persons will suffer from the disease. 2. If x is a Poisson random variable with variance 5, obtain number 1 p of x equal to 0, number 2 mod of x. 3. For a Poisson random variable x, p of x equal to 2 equal to p of x equal to 3, find 1 p of x less than 1, 2 p of x greater than 3. 4. A man decided to toss a fair die until he obtains a 1 or 2. Find the probability that he will stop tossing in 6th toss. The books for your reference are Introduction to Probability Models, Sheldon M. Ross, Academic Press, 1997. Introduction to Mathematical Statistics, S. C. Gupta, V. K. Kapoor, Sultan Chand and Sons, 2003. A First Course in Probability, T. K. Chandra, D. Chatterjee, Narosa, 2003. A First Course in Probability, Sheldon M. Ross, Pearson Education, 2007. Probability and Statistics for Engineers, R. A. Johnson, PHI, 2005. Hope you enjoyed this session. See you next time. Until then, goodbye.